And now let me ask the next person, who is Ronaldo Vieira. Please, Ronaldo, show yourself and your screen.
Let me do this here. I'll share this
Share
one.
screen.
Okay,
Yes.
can you see the
and the presentation, full
presentation?
screen
Yeah.
mode may be
Okay.
better. Okay, so
Is it
levitating atmospheres around naked singularities. Please welcome.
Can you hear me well?
Yes.
So good afternoon. I'm Ronaldo Vieira from the Federal University of ABC in Brazil. And today I'll talk about levitating atmospheres around naked singularities. This work has been developed with Professor Wojciech at the Copernicus Center in Poland. So in order to talk about levitating atmospheres around naked singularities, we need to know what is a levitating atmosphere and what is a naked singularity, so then we can talk about it. Well, in a nutshell, what I'll present is contained in this slide. So we know atmospheres around the star in Newtonian gravity. I mean, we have a star and we put a test fluid which will describe an atmosphere with some radial dependence of density and pressure, and we do it by solving the equation of hydrostatic equilibrium. And the result, the qualitative result, is that the atmosphere is denser near the stellar surface, and it falls with radius into some place. And what happens with a spherically symmetric naked singularity is not this. I mean, suppose this black dot is a naked singularity, which I'll say what it is in a few seconds. What happens is that gravity itself will prevent the atmosphere, the same atmosphere, gravity will prevent it to go up to the singularity. There will be a radius, inside radius, inside which there will be no matter, so the atmosphere will be at a positive distance from the singularity. So gravity itself will hold the atmosphere apart from the singularity. And this is what we call a levitating atmosphere. And then it will have a density and pressure profile depending on the equation of state, with a peak at a certain radius, which is not at the center of the space-time. How do we do it? I mean, I need to define what is a naked singularity. What we will call a naked singularity is a singularity which is naked, right? It's the best definition for a naked singularity, a singularity which is naked. So what is a singularity? I'll say that a singularity will be a region of space-time at which curvature invariance goes to infinity, meaning that even either one of them goes to infinity at least. Either the Ricci scalar or the Crashman scalar or any other scalar which is constructed with curvature, the curvature tensor goes to infinity. And then the classical Einstein's equation is not valid anymore, and we have to do something else, which is beyond the scope of this talk. And the singularity is naked. What is the naked part? I mean, we know that in general relativity, there's a cosmic censorship conjecture, which says that every singularity has a horizon. I mean, there are black holes, and the black holes have horizons, event horizons. So an external observer cannot see what happens inside this event horizon. So an external observer cannot see what happens at the singularity. And it means for a spherically symmetric metric that the GTT never goes to zero, because horizons are for spherical symmetry where GTT goes to zero. Good. So I'll show some nice diagrams from Katka, which show what happens with a black hole and a naked singularity. So those are embedding diagrams of the spatial part of some static spacetime, spherically symmetric spacetime. So what we do with an embedding diagram is that we put we translate the spatial part of the metric, which is curved, onto a 2D surface in 3D Euclidean space with the same, which shows basically have the same curvature of the metric. So for a black hole, we see that the embedding diagram shows the curvature of the metric, of the spatial metric, growing, and it stops at the event horizon, which is here. I mean, it goes vertical. And for a naked singularity, there is no event horizon, so the embedding diagram goes up to the singularity. But what is interesting is that for a wide class of spacetimes, there is a region around the singularity inside which gravity may be called repulsive. If I put I'll now say what is a repulsive gravity. So if I get a spherically symmetric metric, we know that the forward acceleration of a static observer has only a radial component, and it is given by phi prime of r. Phi is essentially it is the GTT, logarithm of GTT. So if I plot phi, here's for Reissner-Nordström naked singularity, I'll talk about it. If I plot phi, I see that there is a point at which phi prime equals 0. So at this point, I have acceleration equals 0. So an observer here is geodesic. It is in free fall. So it stays here with no force to keep it. So gravity is attractive on one side and repulsive on the other side. And then force balance is only due to gravity. Gravity itself can create this zero gravity sphere, which is where particles stay at rest. This is different from what happens in luminous neutron stars. I'll talk about also later that in luminous neutron stars, we can have some kind of balance this way, but we would have to put radiation. So now I have this condition, phi prime equals 0. We have the zero gravity radius. And then I want to know if the zero gravity radius is stable or unstable, if particles stay there or they go somewhere else. So the condition is that phi 2 primes at R0 is positive, meaning that this is concave. And then is a potential well, basically. So if matter accretes, for instance, from an accretion disk, if matter accretes this way, it falls the potential well, and then it will stop at this. It will not go up to the singularity. It will stop here. And if it stops here, it starts accumulating. And if it accumulates a lot, then we won't have to, we cannot treat it anymore as a bunch of particles. We would have to consider the pressure of this configuration. And the pressure, so we have a pressure. We would have a density profile here of matter accreted, and also a pressure profile. And this is what we call an atmosphere. So this will be a pressure profile related to this potential. And then it has a peak at the zero gravity radius. And if we see here, what happens is that it is this, it's that figure. I mean, it has a finite radius in the beginning and a finite radius outside in such a way that the atmosphere is levitating, which is different from what happens here in red for Newtonian case. So I'll show some equations of how we do it. And this is basically done with the equation of hydrostatic equilibrium. I have already the metric, so I assume that the atmosphere is described by a test perfect fluid with low temperatures, so we can consider negligible the relativistic effects on density. So this is essentially matter density. And hydrostatic equilibrium is calculated by getting the divergence of T mu nu equals 0. I should say that this is valid for general relativity, and this procedure would be valid only for theories of gravity at which the usual conservation laws of general relativity are true. If it is not true, we have to do something else. So this gives us this equation where phi is not the gravitational potential, but it is a component of the metric. But it's essentially the same equation of hydrostatic equilibrium that we see in Newtonian mechanics, Newtonian gravity. So we solve it, right? We have a polytropic atmosphere, P equals K rho to some gamma, and this is a solution. We calculate, and this is the solution. We have a pressure profile, a density profile, and temperature profile for a ideal gas. It is not so important the form of the pressure, density, and temperature profile, but the fact that it depends on phi of R minus phi of R0. It depends only on the potential. So if given the potential, we have the atmosphere. It is very simple. So I'll show some examples of what is happening. For instance, for Reissner-Nordström spacetime, we know if charge is larger than mass, then we have a naked singularity. So this is charge over mass to -2. This is radius over mass. So if this is less than 1, we have a naked singularity, and we see this black line. This black line represents, this black curve represents a naked singularity. Sorry, represent a zero gravity radius. The white region is repulsive gravity. And then we get some values and we plot the atmospheres, nice atmospheres. We see that they have a qualitative shape, that they grow and then they fall up after the anti-gravity radius. And they have a tail here. They are not symmetric. But if we go to larger, smaller values of rho, then they become more and more symmetric in such a way that in the geometrically thin case, it is symmetric. And we can do it for any kind of spherically symmetric naked singularity spacetime, which has a zero gravity radius. So we do it for Kehagias-Sfetsos spacetime from the Rojava gravity, which was well covered in Sudipta's talk. So I'll just show the metric and show that the same thing happens here. We have a naked singularity, we have a zero gravity radius, and we have inside repulsive gravity region. And we have basically the same structure for density and pressure. It grows, it falls, and has a tail. So what is interesting? Let me come back. So what is interesting is that here we have the tail of the atmosphere. And as I said, as we go to smaller densities, the tail gets smaller, so it stays quite symmetric with respect to the anti-gravity radius. So let's calculate the geometrically thin approximation. As I said, pressure and density would depend only on phi of r minus phi of r0. So if we expand it in Taylor series and get the first term, it will be phi 2 primes of r0 times this. So P of r will depend on phi 2 primes of r0, and this will be the only parameter which describes the spacetime. Given a spacetime, I get r0 and I have phi 2 primes of r0, and this is a number. So spacetime now doesn't give us a function but a number. So in the geometrically thin approximation, we would have a number which describes the spacetime, and then if I have a different spacetime, I have a different number. So what it means that in geometrically thin approximation, all the atmospheres will have the same radial dependence of all spacetimes. Any spacetime I put here with a zero gravity sphere will have the same shape. I would like to make a small comparison with luminous neutron stars. So we know that in Newtonian gravity, luminous neutron stars has no levitating atmospheres. In GR, near Eddington luminosity neutron stars, we know that have levitating atmospheres, but those levitating atmospheres are not given only by gravity. I mean, gravity will be always attractive, so there should be something which is repulsive, and this repulsive thing is radiation pressure, the radiation force on the particles. So it has a different radial dependence than the gravitational field. So what happens is that there will be an equilibrium radius, and atmospheres around this equilibrium radius would give us some profiles which may or may not be different from what a naked singularity. So radiation pressure is dissipative, what means that oscillation modes of levitating atmospheres around neutron stars will be damped. If I perturb the atmosphere, this perturbation will vanish with time. So for naked singularities, it doesn't happen because there's only gravity, which is a conservative force. So oscillation modes in naked singularity spacetimes, in naked singularity atmospheres, levitating atmospheres will be not damped. They will live forever. It will bounce forever unless there's a viscal force in the fluid. So to finish, I would like to draw some conclusions regarding what I said. Some things I will repeat, some things I will not repeat. I will say now. We found general expressions for any naked singularity, spherically symmetric with a zero gravity radius. And those expressions represent levitating atmospheres. If I perturb the atmosphere, there will be no damping in the oscillation modes. As I said, they live forever except for viscous forces in the fluid. So this no damping condition may be a signature of naked singularity, meaning that for neutron stars, we know that there will be damping. So if there is no damping, we don't see damping, it may not be a neutron star. So, it is important to remark that this is true not only for naked singularities, but it is also true for any spherically symmetric spacetime which has a stable zero gravity sphere, because we don't look at what happens in the center of the spacetime, in the center of the coordinate system. We only look at what happens in the vicinity of the zero gravity radius. And this is not dependent on singularities or whatever I have a compact object, strange object I have inside. So another thing is that since there is only gravity in the balance, there is no radiation, things will be the same for optically thin and optically thick profiles of the levitating atmosphere. So there is a question, perhaps it is optically thick. So can naked singularities wander around the universe, dressed, not naked, but dressed, with an optically thick atmosphere, so it looks like a gaseous planet? It doesn't look like any more singularity. We don't see the singularity, we stop at the surface of the atmosphere, so we see a gaseous planet, basically. We don't know. And since there is accretion, and accretion will stop at this anti-gravity radius, it will not reach the singularity. And once it stops, the levitating atmosphere is inevitable. Accretion will create it. And therefore, the singularity will be dressed and not naked. It will be dressed with, an atmosphere, a gaseous atmosphere. And then the question is, can it be observed? Can singularities be dressed? Can we see singularities? Well, this is it. Thank you.
Thank you very much. Very interesting presentation. Are there questions, please? Iji, please ask your question.
Yeah. Hello, Ronaldo. Very nice. Thank you. Thank you. I have a question. So this like gravity sphere, zero gravity sphere, is defined only for kind of static observer, right? So I wonder what would happen, like, could I have like accretion disk around this naked singularity, or how it would look like? It would have inner edge where the matter will be accumulated.
Yeah, this is very interesting. May I come back to the slide? This slide. So what happens, and this is something which was done for many spacetimes by Zdenek. Zdenek worked a lot on this, and also Yanqi and other people from Opava group. What happens is that once matter accretes, well, the accretion disk profile depends essentially on the angular velocity of the circular orbits of a geodesic, right? So if the angular velocity goes to 0, it means that there will, for a thin accretion disk, there will be what would be an ISCO, but it's not an ISCO anymore because we don't have ISCOs. What happens is that when we go through this point, matter accretes. At this point, the zero gravity radius, there is this condition that, well, I mean, it is true that the angular velocity of such particles goes to 0 at this radius. And well, if it goes to 0, the angular momentum goes to 0. What happens is that at this radius, the angular velocity goes to 0. If the angular velocity goes to 0, this will be an inner edge for an accretion disk. As I said, many papers of Zdenek and his collaborators were about this, and he can talk about better some observational properties of naked singularities based on what happens here in this region. So this is why accretion stops here. It's because it will be the inner edge of the accretion disk.
Okay, thank you.
And Maciek Wielgus has a question.
Hello. So my question is, wait, I need to organize my thoughts. The first question and I forgot the second, but I will ask first. So the first question is: I understand you work in this Hojava Kehagias-Sfetsos metric, right?
Yes. Also.
So, and it's interesting that it would, you know, stop the accretion. That it means these naked singularities would not really accrete. So.
Yeah.
I mean, it would stop at the surface. And do you know if this is like more general property, or is this very specific to this Kehagias-Sfetsos? Like if I had super spinning naked singularity, would it also have this property?
Well, I can answer this in two ways. The first way is simple, is I don't know.
Okay.
The second way is that I can explain. So what happens is that we work with a very special case, which is a spherically symmetric spacetime. For any, and this is general inside the particular case. If I have a spherically symmetric spacetime with a zero gravity radius, not only Kehagias-Sfetsos, but Reissner-Nordström naked singularity, or any other naked singularity with a zero gravity radius in a different theory of gravity, it will mean that, I mean, basically, if it is spherically symmetric, as it, and if phi has this form, qualitative form, we have this property of having being able to construct.
Yeah. This of course I see, but you are not saying that any spacetime of a naked singularity that is spherically symmetric will necessarily possess this property of having this zero gravity surface. This is not your claim.
This is not my claim.
Okay,
my
good.
claim is that any naked singularity spacetime that I know has this property. I cannot say for it.
Good. So it's any interesting exercise to check it out for, like yes, super spinning care or something like that. And and now I remember my second question. It was good to speak for a minute about the first one. So I wonder, but I guess these atmospheres can thicken out, become more and more thick geometrically. When there is more and more matter. So can it, is it fine if at some point it will actually hit the zero radius and at some point it will accrete? Meaning, you know, it's so thick that it extends all the way to zero R. Is that?
Yeah, I'll first answer the current case.
Oh, okay.
It may happen, we don't have radiation, so we don't have to model the radiation field. But we have gravity. So what happens is that if there is an equilibrium surface of the gravitational field there, which is not symmetric, spherically symmetric anymore, but if it has another shape, then there will be an equilibrium surface, not anymore a radius, and which is this distorted surface, like this, not spherically, but the atmosphere will be distorted. Maybe distorted, let's put this way. And then there will be some kind of atmosphere around a static distorted spacetime. But as you have shown for the case of rotating spacetime with radiation, rotating neutron star with radiation, we don't have this surface, we have a ring. So I don't know if we put rotation here, there will be a surface or it will break into a ring. So there will be an atmospheric ring around the singularity. And
I think we have to go on.
So,
if you want to ask another question or continue discussion, just please write on chat.